understanding of the first concept is of the microoperation. So what is it? The execution of program that consists of the sequential execution of instructions, and each instruction is executed during an instruction cycle which is made up of the shorter sub-cycles. For example, as we have studied, the fetch, indirect, execute and interrupt. The performance of every subcycle that involves one or more shorter operations, that is micro operations. So these are the functional or atomic operations of a processor. Like we can see from the diagram, the program execution has instruction cycles to n, which can have the further parts as fetch, indirect, execute and interrupt. If we talk about the fetch cycle, we can have that there are four types of registers are involved. The first is memory address register, the second is memory buffer register, third is program counter, and the fourth is instruction register. So the memory address register is connected to the address line of the system bus, and it specifies the address in the memory for a read or write operation. If we talk about memory buffer register, it is connected to the data lines of the system bus and contains the value which has to be stored in the memory, or the last value read from memory. If we talk about the program counter, it is able to hold the address of the next instruction to be fetched, and the instruction register is used to hold the last instruction that was fetched. We can have an example, like we can look at the sequence of events for the fetching of cycle from the point of view of its effect on the processor register. Like the example you can see, in the beginning it was in the PC, then it moved to the MAR, BAR also, and in the third step, if we talk, MAR, BC, MBR and IR, they both are failed like this. So at the beginning of the fetch cycle, the address of the next instruction to be executed in the program counter is 11001000. The first step is to move the address of the MAR, because this is the only register which is connected to the address lines of this bus. If we talk about the second step, it is to bring in the instruction, and the desired address is, we can see from the diagram, the control unit that issues a read command on the control bus, and the result that appears on the data bus, it is copied. In the MBR, that is memory buffer register, we also need to increment the program counter by 1 to get for the next instruction, because there are two actions in reading from a memory and adding the one to PC. They do not interfere with each other. We do them simultaneously for the saving of time. The third step is to move the contents of the MBR to the instruction register, and the phase is up to the MBR for using a possible indirect cycle. So this is the sequence of event as follows, where MAR is less than equals to PC. In the second, MBR is less than equals to memory. The PC is less than equals to PC plus 1, and IR is less than equals to MBR. Similarly, we can have the instruction length and the other one. In the next slide, we can see our next heading is indirect cycle. Indirect cycle is, we can see, once an instruction is fetched, the next step is to fetch the source operand, and continuing our simple example. We can see, if we assume a one address instruction format with the direct and indirect addressing allowed, if the instruction specifies an indirect address, then an indirect cycle that must precede the execute cycle. So the data flow that includes the following operations. Like for T1, we can have MAR is less than equals to IR, second, MBR is less than equals to memory, and the third, IR is less than equals to MBR. So the address field of the instruction is transferred to the MAR, and this is used to fetch the address of the operand. So finally, the address field of the IR is updated from the MBR, so that now it can have a direct rather than an indirect address. If we talk about the interrupt cycle, you can see at the completion of the execute cycle, a test is required to determine whether an enable interrupts have occurred. If it is so, the interrupt cycle occurs. So the nature of the cycle varies greatly from one machine to another. We present a very simple sequence of the events like T1 is showing MBR is less than equals to PC, T2 MAR is less than equals to save address, third PC is less than equals to routine address, and the T3 memory is less than equals to MBR. In the first step, the contents of the PC are transferred to the MBR so that they can be set to return from the interrupt, and then the MAR is loaded with the address at which the contents of the PC has to be saved. So these two actions may be each a single micro operation like this in the same manner. If we move to the execute cycle, the execute cycle is what? The fetch, indirect, and interrupt cycles are simple and predictable, and each of them involves a small fixed sequence of the micro operations. In each case, the same micro operations are repeated each time around. If we talk with the example, we can see to consider an add instruction can have add R1, X, which can add the contents of the location X to the register R1. And the following sequence of micro operations might occur, like T1 can show MAR is less than equals to IR, T2 shows that MBR is less than equals to memory, and the T3 shows R1 is less than equals to R1 plus MBR. If we begin with the IR that is containing the AND instruction, in the first step, the address portion of the IR is loaded into the MAR, and then their reference memory location is read. So finally, the contents of R1 and MBR are added by the ALU, and again, this is a simplified example. The additional operations may be required to extract the register reference from the IR and perhaps to stage the ALU inputs or outputs in some intermediate registers. So we have another sequence of the micro operations in this slide. If we move to the instruction cycle, we can see in the instruction cycle, we have already saw that the each phase of the instruction cycle that can be decomposed into a sequence of elementary micro operations. We can have example that there is a sequence for each of the fields in the and interrupt cycles, and then for the execute cycle. So there is one sequence of micro operations for each output. To complete the picture, we need to tie the sequences of micro operations together. As this is done in the figure, you can see there is ICC that is going with the 10 execute and 01 indirect to the read address line, and the interrupt, disrupt are there. You can easily see from the diagram. If we assume a new bit register that is called the ICC, that is instruction cycle code, the ICC designates the state of the processor in the terms of which portion of the cycle is in. 00 is for fetch, 01 is for indirect, 10 for execute, and 11 for interrupt. So at the end of each of the four cycles, the ICC is set appropriately, and the indirect cycle is always followed by the execute cycle. So the interrupt cycle is always followed by the fetch cycle. For both of the execute and fetch cycles, the next cycle depends on the state of the brick system. So the flowchart of the figure defines the complete sequence of micro operations, and depending only on the instruction sequence and the interrupt pattern. So now moving to our next topic, that is hardware implementation of CPU with the micro instructions. To execute an instruction, the control unit of the CPU must generate the required control signal in the proper manner or sequence. So there are two approaches that are used for generating the control signals in proper sequence as the hardware control unit and microprogram control unit. If we talk about the hardware control unit, you can see from the figures, this figure, easily there are flags and variables in the next control state generator. There are external signals that are generated by the control signal generation matrix, and For the computer units, there are instruction registers for opcode, address field, instruction decoder, and there is a timing unit that is regular signal from the path generator. So, if we talk about further procedures, the control hardware that can be viewed as a state machine that changes from the one state to another in every clock cycle, which is depending on the contents of the instruction register, the condition code, and the external inputs. So the output of the state machine are the control signals, and the sequence of the operation that is carried out by this machine is determined by the wiring of the logic elements, and that is why it is named as the hardware. So the fixed logic circuits that corresponds directly to the Boolean expressions are used to generate the control signal. So the hardware control unit is faster than the microprogram control unit, and a controller that uses this approach can operate at a high speed. An RISC architecture is based on the hardware control unit. If we move to the microprogram control unit, you can see the control signals that are associated with the operations are stored in the special memory units that are inaccessible by the programmer as the control words. So the control signals are generated by a program that are similar to the machine language programs, and the microprogram control unit is slow in the speed because of the time it takes to fetch the micro instructions from the control. If we talk about some important terms, they are like control word. It is a word whose individual bits represents the various control signals. So there is a microroutine, that is a sequence of the control words that are corresponding to the control sequence of the micro instruction that constitutes the microroutine for that instruction. If we talk about the microprogram, it is a sequence of micro instructions which is stored in a ROM or RAM. So it is also called a control memory or CM. If we talk about the control store, the micro routines for all the instructions in the instruction set of a computer are stored in a special memory called as the control store. So we can see from the diagram there is a control store which is connecting to the micro instruction address register with the help of decoder, and it has its own operation paths control address which has for that DEC1, DEC-P control signals, and from the main memory we have the opcode instruction register at address. So if we talk about the types of microprogram control unit, it is based on the type of the control word that is stored in the control memory and classified of two types. The first is horizontal microprogram control unit. In this part, the control signals are represented in the decoded binary format, that is 1 bit per second. For example, if 53 control signals are present in the processor, then 53 bits are required. So more than one control signal can be enabled at a time. It is able to support the longer control word used in the parallel processing applications, allows the higher degree of parallelism, and requires no additional hardware. And it is more flexible than the vertical microprogram control unit. If we talk about the second type, that is vertical microprogram control unit, the control signals are represented in the encoded binary format. For the N control signals, log 2 N bits are required. It can support to a short control words. It supports the easy implementation of the new control signals, so it is more flexible. If we talk about the degree of parallelism, it is either 0